Hello, and thank you for attending to this presentation. My name is Rodrigo Castellanos. I'm PhD candidate at Universidad Carlos III de Madrid, and in the following minutes I will be shortly presenting you my last work titled Machine Learning Flow Control in the Few Sensor Limit. So to start with this presentation, let me start with the objective of the presentation itself, or the work itself, which is to investigate strategies to control shedding flows in the few sensor limit. In particular, we will focus on the conventional to the cylinder flow. And here the keyword is the few sensor limit, which is the main motivation of our study. Basically because any active flow control strategy that is generated is hardly applicable in the real world due to difficulties commonly based on hardware. So reducing the number of probes while keeping an effective and efficient control strategy is very relevant both for industrial application but also for experimental research. But how are we going to find this flow control strategy? Well, here we want to investigate two strategies and we will compare them. They are very well known machine learning methods, which are reinforcement learning and genetic programming. And here I will shortly explain you in a very visual way how they work. Reinforcement learning is a training process through which we want to train or adjust an agent given a certain plant, which in this case is a simulation. The agent is kind of the brain that tells us which is the best action that we have to perform given a certain state given by the simulation. Eventually the agent is a neural network, so the training process consists on adjusting those coefficients of the neural network to finding the optimal configuration. But note that the agent is not only based on the state but also on the reward, which is telling us how good or how bad we are doing in the training process. In particular, when the reward tells us that we are doing bad, like for instance in this example of a robot learning how to walk, it tells us that we are growing in the wrong direction, so we stop exploring in that direction. If the reward is positive, this means that we are learning how to do it. That could be the second example here. If we keep progressing and do it episode by episode, so doing the loop again and again, we can conclude and learn which is the best agent configuration for the problem that we want. In the other hand, we have the genetic programming. It is based on evolutionary algorithms. So what we do here is to have a bunch of individuals, each individual representing a control strategy, and we evaluate all of them. Eventually we will find which is the best individual, generate a new population of them, and evaluate again, and so on and so forth till we find convergence and the best individual of the problem that we are working. So here you have an example of several individuals that are evaluated, all of them together. Those ones in orange are the best individuals. Here I randomly selected 5 of them that are the ones that will be selected for the next population as elitism. That means the n best individuals, and the rest of them are banished, and we generate new ones by a genetic operation that could be mutation or crossover. So the frameworks that we are going to use for this work are the framework proposed by Rabault and co-workers in the Journal of Fluid Mechanics paper from 2019 in the case of reinforcement learning. They use a PPO method to learn the neural network coefficients. And in the case of genetic programming, I will use the XNLC framework, which is a MATLAB-based code using the linear genetic programming. And the main target of this computational tool is to evaluate and evolve populations to find the best individuals. And these individuals are presented as control strategies in terms of what they are analytical expression as a function of the sensor that we will see in a minute. So which is the environment, which is the plant that we are using to train our models? Well, it is a very simple simulation. It's a 2D cylinder flow. In particular, we are using the framework proposed by Rabault and co-workers in the paper that I said before, that is an adaptation of the well-known benchmark by Schaffer and Turek. In particular, this simulation is a DNS based on Phoenix open source software. Here we keep the Reynolds number quite low, 100 based on the diameter, and the domain is 22 by 4 diameters. Regarding the sensor and actuators, we are using 3 different configurations, that is 5, 11 and 151 only for reinforcement learning, but these are locations, and I say locations because at each of these points we are having not only one but 2 probes, one for horizontal velocity and one for vertical velocity, and this would be our sensing. For reinforcement learning, by its nature, we are keeping the temporal evolution of these sensors somehow, and that means that when we are passing from one episode to the next one, we are adjusting the model, we are adjusting the agent, and that means that we are somehow keeping the information from before, but also we are learning from the future due to the expected reward. In the case of genetic programming, this is not happening because when we evaluate one individual, it has nothing to do with the other ones commonly. So we are not tracking, which is the time history of or temporal evolution of our sensors. So in order to add this time history, what we decide to do is to add fictitious sensors at different time steps or time instants, which are the current time instance minus half of the shedding cycle, 1/4 of the shedding cycle, and 3/4 of the shedding cycle. Regarding the actuators, we are using two mini jets, here depicted as a blue triangle on top and the bottom. They perform suction and ejection operations, but with a zero net mass flow. That means that, for instance, if the top one is injecting mass, that means that the bottom one is sucking mass with the same mass flow rate. And in terms of the state, we will evaluate it with two figures of merit, which is the drag and the lift coefficient, that tell us good enough how the flow is oscillating and also how it is evolving in terms of our cost function that is defined as here you see. The main target is to minimize the drag coefficient, but not only that, we add a regularization term in here in order to have a symmetric solution, or at least as symmetric as possible. That means having the mean CL value equal to 0. So the first study that we perform is a convergent analysis, and for this we want to keep a fair comparison. That means in terms of reinforcement learning, having the same number of episodes, and in terms of genetic programming, the same number of total individuals. Each episode corresponds to launching one simulation, and in the case of genetic programming, each individual represents launching one simulation. So we are evaluating in the limit of the same computational cost. So what we see in this figure showing us which is the drag coefficient reduction as we evolve in the number of episodes or individuals, is that reinforcement learning converges quite fast. In the case of 500 episodes, we already have convergence for the case of 11 and 151 probes of reinforcement learning. However, in genetic programming, it takes us quite longer. However, we reach a higher reduction. This is something that we also see in terms of the cost function, in which we add the lift coefficient. And in here we see that reinforcement learning needs, in the case of 5 probes, a little longer to converge. Anyway, it is way faster than genetic programming. Here I show you which are the winning strategy for each of the cases. In particular, for the cases of 5 probes, both genetic programming and reinforcement learning, they perform very similar. They reach a drag reduction which follows a very similar path in terms of temporal evolution, with an average reduction between 3.5 and 4%, as we saw before. And in terms of lift, we modify the characteristic frequency of the system, but also we reduce the amplitude of the lift oscillation. Focusing on the reinforcement learning cases for 11 and 151, it is true that we reduce quite a lot the drag, up to 7-8% reduction. However, what we see is that the lift coefficient oscillates around a mean value that is not equal to 0. That is, we have an asymmetric solution. This is not surprising because we saw already these kind of solutions in the literature. However, our best solution here is the one for XMLC at 11 probes. So let's have a closer look at this one. Eventually, what we see here is a rather simple control strategy proposed by XMLC. We are having only 3 probes out of the possible 22 of them. Remember that we have 11 positions but 2 possible values at each of these locations. And this is characterized by a strong actuation at the very beginning that pushes us to a different attractor of the dynamical system. And once we are close to this attractor, the actuation is very tiny, very small, so a low energy consumption that allows us to keep the CD very stable. The shedding is almost vanished, and this we also see this in terms of the CL. So just to finish, let me read the conclusions that we can draw. Both reinforcement learning and genetic programming are capable of finding suitable control actions for the proposed problem. However, reinforcement learning converges way faster, and genetic programming reaches better performance with a few number of sensors, which is very good. This tells us that XMLC stands as a computational tool for designing fault control experiments, telling us which is the best number of probes, but not only that, but the locations prior to doing the experiment. So thank you very much for your attention, and if you have any question, contact me by email.